Assalamu alaikum. How are you, everyone? I hope everyone is fit and fine. I will try my best to go live to discuss some of the research papers with you. In a brief, we will start. I want to review a series of papers, how to read the paper and how to understand the results and how to get a conclusion and how to report these results in your own research paper as the background of the research, or sometime we need to write a review paper, so this information can be helpful for these purposes. So today, friends, I'm here presenting a paper. The paper is published in Applied Catalysis A General, has a good impact factor, and the series, a journal of the elsewhere series, and the topic is synthesis of BiOBr, or carbon quantum dots microsphere with enhanced photocatalytic activity or photostability under visible light irradiation. So this is a very beautiful topic, and it is based on the sustainable and the green energy that's using the light. So what the researchers have done in this paper, that this paper, the BiOBr and carbon dots microsphere were successfully synthesized by the authors who work on this paper with the facile solvothermal, a hydrothermal method. And the structure of the morphologies of the optical properties of the photocatalytic performance were investigated in the detail. The research showed that the BiOBr and carbon quantum dots microsphere exhibited a significantly enhanced photocatalytic performance as compared with the pure BiOBr when carbon quantum dots introduced with appropriate the highest photodegradation rate 0.0296 per minute. This rate was achieved would be obtained in the photocatalysis process, and rhodamine B. It is an organic pollutant, water pollutant, which was it could be could be about 5.3 times higher than the pure BiOBr visible under visible light irradiation, and as well as the for p-Nitrotoluene (PNP) photocatalytic activity. This photocatalytic system, the enhanced photocatalytic activity, was mainly attributed to the fast interfacial charge transfer ability and enhance the light harvesting for appropriate carbon quantum dots introduction. So actually this is the short abstract. Abstract is a very short summary in which you just describe the methods and the procedures how you get some good results. Here we not discuss anything. So this is the abstract. Means we have to keep in mind that it's integration between BiOX, that's especially BiOBr, and carbon quantum dot microspheres. In the introduction, Intercenter photocatalysis technology offers the green technologies for the complete elimination of the various kind of contaminants, and especially some of the dyes and containing ideal hydrogen energy from the sunlight and water. So considered as a very important method for relieving or resolving the current environmental issues and energy crisis, particularly the bismuth halide BiOX, BiOX is ClBr and I, who have been widely studied due to their excellent photocatalytic properties and the catalytic performance. Among the numerous BiOX semiconductors, BiOBr was correctly investigated for its appropriate band gap and excellent visible light photocatalytic activity. However, the photocatalytic activity of the pure BiOBr semiconductor was limited by its low suppression efficiency of photoexcited electrons and hole pairs. In order to improve the photocatalytic activity, BiOBr semiconductor, the BiOBr has modified by SiO2. So we have to modify this Fe3O4 or MSiO and MOS2, BiOI, Bi24 O31, Br10. NiFe2O4 or BiOBr, WO3, Bi2, WO6, Bi2O3, nitrogen doped graphene, BiOPO4, TiO2, Bi2O, WO6, and Ag3PO4, CO, Fe2O4, CDS, and H2CO3, etc. However, these large size materials can hardly be built perfect interacted interfaces with BiOBr. The surface defects could act as recombination centers for photoexcited electrons, hole pairs, which may limit the photocatalytic activity. And carbon quantum dots, a new class of the carbon nanomaterial with a size less than 10 nanometer, was first obtained during the purification of the single-walled carbon nanotube through the preparation of electrophoresis in 2004. The group newly emerged fluorescent nanomaterial carbon quantum dots have shown tremendous potential as versatile nanomaterial for a wide range of application, including chemical sensing, biosensing, bioimaging, drug delivery, photodynamic therapy, photocatalysis, and electrocatalysis. Compared with the conventional semiconductor quantum dots, the unique attribute of the carbon quantum dots, for example, being chemical and com composition, chemical composition, tunable fluorescent emissions, facile functionalization, and excellent physicochemical and photochemical stability, non-photo bleaching or non-photo blinking, render them very attractive for the technical application. Together with the other advantages such as low cost and ease of synthesis, carbon quantum dots are in a favorable position for achieving unprecedented performance. Carbon quantum dots are typically quasi-spherical and nanoparticle comprising amorphous or non-crystalline core with the predominantly graphite uh, or turbostatic carbon sp2 carbon and graphene oxide sheets fused by diamond like sp3 hybridized carbon insertions, which provide carbon quantum dots with a superior electron transfer and reservoir ability. In addition, converted for photoluminescence and PL behavior current dots can be expand the light utilization range of the nanomaterial from UV to visible range and enhance the photo induced electron transfer. Therefore, a series of carbon quantum dots based on the photocatalysts have been synthesized to improve the photocatalytic activity of semiconductors, such as carbon quantum dots over copper oxide, carbon quantum dots over Fe2O3, and carbon quantum dots over BiO2MO6, carbon quantum dots over TiO2, and carbon quantum dots over Ag3PO4. And from the between carbon quantum dots and semiconductor, as well as the functional mechanism of the carbon quantum dots for photocatalytic activity improvement is far from clear. Therefore, it was highly desirable to solve the problem of aforementioned in order to further improve the performance of carbon quantum dots by appropriate means, so as acquired satisfactory high efficient photocatalytic activity of carbon quantum dots based material. Considering the superiority of BiOBr and carbon quantum dots above mentioned, the BiOBr carbon quantum dots microsphere was successfully prepared via facile hydrothermal route followed by the hydrothermal process. The structure of the morphologies, optical properties were investigated in detail, and the photocatalytic activities of BiOBr and carbon quantum dots material were evaluated sufficiently by the photocatalytic degradation of two different kinds of the model pollutants, RB, HB, rhodamine, B, and phenol, and the relationship between a structure uh, the relationship between the structure of the photocatalyst and the photocatalytic activities were also discussed in detail. Ultimately, the mechanism of pollutants degradation in the system was studied. So this is a background of the paper in which different uh, background were discussed, that how to find out the suitability of the solution, how to address the problem. In this part, we will discuss here the results and discussion, because this is our man, and at the end we will go through its short instrumentation too. Results and discussion. The compositional and structural information, the phase of the BiOBr and carbon quantum dot microsphere with the different carbon quantum dots content were investigated by X or D. And direction spectra was shown. The peaks obtained 10.9, 25.3, 31.8, 33 point. So these all are the peaks which are received by XRD. So this is the XRD result. Later I will show you the, first we will just read the results. The crystal planes of tetragonal BiOBr respectively, and its JCPDS. Actually, this is the international uh, data base for the XRD salts and the crystals. So we must take a reference from this data, and we have to put our data and compare according to this data. After introduction of carbon quantum dots, some of the new peaks appear. That's 23, 27, 38, and 39, which could be indexed as 101, 10012, 0104, and 110 crystal plans of the rhombohedral BI. That is also JCPD card number 441264. It should be transformed from the BiOBr matrix during the growth process. The carbon quantum dots under high temperature and pressure and maybe exhibit the superior surface plasma resonance effect of the photocatalytic process. Furthermore, the diffraction peaks 100 and 20 and 10 crystal plans of 46.91 and 51.97 respectively. So these are some crystal planes with the red shift. It indicates that the interacted interfaces were successfully formed between BiOBr and carbon quantum dots. No typical diffraction peaks of carbon quantum dots detected, which could means in this just peaks with some different morphologies received, but it is a successful junction between these two materials. Can be explained with the lower amount of BiOBr quantum dot material. Similar results have been found in other systems, because there are different studies which also present the same type of data. Furthermore, XPS spectra of BiOBr and BiOBr carbon quantum dots microsphere were used to confirm the elemental composition and valence state. The survey spectra indicates the BiOBr contains BiOBr elements, while the BiOBr carbon quantum dot material contain all aforementioned elements except Br. It can be attributed to the reduction amount of the Br element due to the conversion of the process of BiOBr to elemental Bi, which would weaken the signal of Br. In addition, work carbon quantum dots on the BiOBr surface may hinder the detection of Br. As the high resolution spectra of Bi, two peaks. Actually, this is now we are discussing about binding energies, elemental composition, and binding energy. So, two peaks located at 159.1 and 164.6 electron volt can be assigned for Bi 4F7 by 2 and Bi 4F5 by 2 of Bi plus 3 in BiOBr. Respectively, in BiOBr quantum dots material, the peak of Bi 4F shift from 156.7 to 162 and 160 electron. So there is a little change in their peaks. They are shifted respectively. Further, more the peaks located at 157.5 and 162.7 electron volt can be attributed to Bi for F7 by 2 and for F5 by 2 of elemental Bi respectively, which is consistent with the results of XRD. Oxygen spectrum of BiOBr can be fit into three peaks located at 530, 531.2, 531.2.1 electron volt can be fitted into which attributed oxygen in BiOBr and other compounds such as OH and H2O. While the oxygen 1s peak is in BiOBr, carbon quantum dot material shift 527.2 and 527.7, 29.7, 531.2 electron volt respectively. BR 3D spectrum in BiOBr can be fitted into two peaks located at 68.2 electron volt and 69.2 electron volt, while BR3D peaks in BiBor carbon quantum dot material shifted to 65.5 and 66.6 electron volt respectively, indicating the existence of interaction between the interfaces of carbon quantum dots and BiOBr. Display high resolution XPS of carbon in sample. The peaks 281.8, 282.9, 285.6 electron volt can be assigned adventitious carbon species from XPS measurements, while the peaks located at 282.6 and 283.9 and 286.4 can be attributed to carbon-carbon single bond, carbon-carbon double bond, and oxygenated carbons and nitrogenous carbon for C1 in BiOB or carbon quantum dots material, respectively. The XPS analysis indicates that the intimate integration of carbon quantum dots of BiOBr was attributed has been constructed in BiOBr carbon quantum dots through material. However, the FTIR spectra of BiOBr and BiOBr quantum dots material was different. Current quantum loading amount, the peaks of uh, at 510 centimeter associated with the BiOBr stretching mode and BiOBr material, whereas the shift at 548 per centimeter and respect to BiOBr carbon quantum dot sample, indicating the existence of the interaction between carbon quantum dots and BiOBr, and BiOBr carbon quantum dots material absorption peaks assigned to absorption peaks of C double O minus appear at 1388 per centimeter, revealing the existence of carbon quantum dots in addition to the absorption peaks located at 3432 per centimeter and 2922 per centimeter can be assigned to the stretching vibration of oxygen hydrogen and carbon hydrogen bonds. FDR results show the carbon quantum dots and BiOBr had been successfully coupled together with the consistence with XPS analysis. Besides, thermal gravity analysis was carried out to further determine the presence of carbon quantum dots in BiOBr carbon quantum dot material as shown, and the trace weight laws have been 100 degrees centigrade can be attributed to the physical absorption in water and the sample. During the growth process of carbon quantum dot, the porous structure was formed in BiOBr matrix, which have been demonstrated by N2 desorption-adsorption characteristic. With the increased carbon quantum dots introduction in the bit surface area would increase accordingly. In the table 1, we will see later. Thus, more water vapors would be absorbed on the surface of the sample. The weight loss at range of 100 to 200 degrees centigrade could be attributed to loss of the sum of small molecules. The weight loss of the samples from 200 to 500 centigrade might be ascribed to the introduction of carbon content dust. In addition, the total weight loss ratio is 4%, 2.6%, 4.8%, and 6%, and at 7.3% and 10.9% BiOBr carbon content dots. Its detailed discussion increasing from 0 to 1.0, and the weight loss increases with the increase of the introduction of carbon quantum dots amount, which demonstrate the carbon quantum dots have been introduced successfully. Curve of theogrametric curves of BiOBr and carbon quantum dots material in the air atmosphere shows the weight loss curve is similar with those in the nitrogen atmosphere, except the weight loss ratio is higher, which may be attributed to the total removal of carbon quantum dots by sufficient burning. Morphology and microstructure analysis. The morphology of the microstructure of the BiOBr and BiOBr quantum dots material have been characterized by same team and have been shown sim images of BiOBr sample attributed to the respective microsphere, like assembled by number of BiOBr nanosphere and microsphere. Every size is above 3 micrometer, and the TIM images of pure BiOBr shows the some nanosheets can be found from the edge of the sphere-like structure, which can be demonstrated that BiOBr microsphere is composed of nanosheets. High-resolution TIM HRTM images of BiOBr are shown in the figure, that the lattice fringes spaces is to 80 nanometer and to 50.3 15 nanometer, correspondingly to 012 crystal plane and 011 crystal plane of tetragonal BiOBr JCPD 3773 dash 2061 can be observed respectively. And F display the same images of BiOBr carbon dot material compared with BiOBr similar microsphere like morphology, with the average diameter of the about 3 micrometer can be observed, which can be consistent to ultra thin BiOBr nanosheets. These results imply the introduction of carbon dots does not change the main morphology of BiOBr. TIM images is applied to further explore microstructure of BiOBr carbon dot material. Similarly, high TIM images BiOBr material of some of nanosheets can be found with the edges of the sphere-like structure. At the same time, the HRTM images of BiOBr carbon dots show that there is a lot of the dark dots in the diameter of the, it's about 6 nanometer, evenly attached to the surface of BiOBr nanosheet, which implies the carbon quantum dots have been successfully anchored on BiOBr nanosheets, and intimate integration has been constructed. In addition, the density of carbon quantum dot would increase the increase of carbon quantum dot content, as shown in the figure, that the spacing of 0.3 to 0 nanometer to and 3 to 8 nanometer can be observed, which can be attributed to 0.002 crystal plane of carbon quantum dots and crystal plane of Bi. Some carbon quantum dots do not show observed lattice fringes spaces due to the carbon quantum dots are quasi-spherical nanoparticle and comprising amorphous and nanocrystalline core. At the same time, the lattice spacing about 0.28 nanometer can be observed, which agrees well with the crystallographic 0.12 spacing of BiOBr. These are images we will see at the end all figures. Above the results, further demonstration that the carbon quantum dots are successfully loaded on the BiOBr to construction BiOBr carbon quantum dot material. Furthermore, the energy dispersion of X-ray spectroscopy EDS analysis. The figure shows that BiOBr carbon quantum dot sample contains carbon, oxygen, Br and Bi elements, which reveals that the BiOBr carbon quantum dot material have been successfully synthesized. Nitrogen adsorption desorption isotherm of these BiOBr and BiOBr quantum dot material were used for further study their microstructure. The bed surface area of the BiOBr and carbon quantum dot 0.6 and 23 is larger than the pure BiOBr. In addition, for S, and we will So friends, optical जो or electronic, the optical and electronic properties, the factors influencing catalytic performance. So usually evaluated by UV diffuse reflectance spectroscopy DSR shown absorption edges of BiOBr carbon conductor material with the redshift compared with BiOBr and means the optical absorption of the visible light is enhanced. The DSR results suggested that the carbon conductors may play important role in the utilization of visible light and such to produce more photoexcited electron and hole pairs. The band gap of the BiOBr carbon conductor material were estimated via classified top material become smaller than the BiOBr. The narrower the band gap means higher photocatalytic performance in the visible light. Photoluminescence performance or the photoluminescence spectroscopy intensity and the lifetime of the photocatalysts are capable to characterize indirectly the combination efficiency of photogenerated electron and hole pairs as is known weaker intensity presence of the lower efficiency of electron hole pair recombination and shown in the figure the material are strongly emission peaks concentrated between 370 to 400 nanometer. The excitations wavelength of the 380 nanometer BiOBr will display lower photoluminescence intensity than the pure BiOBr, indicating the decrease in recombination efficiency of electron and hole pair. The phenomena can be ascribed by the high curious transferability between the interacted uh, interfaces of carbon quantum dots and BiOBr, leading to the effective suppression of electron hole pair. So photocatalytic test. The photocatalytic test of as per prepared Br carbon conductor material was first evaluated the degradation of RHP under the visible light, irradiation and absorption and deabsorption. Absorbance was achieved between the catalyst and the dye in 30 minutes before photocatalysis. It has been seen the direct photolysis of the rhodium B is negligible without adding photocatalyst. In the presence of the photocatalyst, BiOBr carbon materials show the higher photocatalytic activity than the pure BiOBr. So BiOBr carbon conduct 0.6 material display the highest photocatalytic activity near to the for rhodium B was degraded by BiOBr carbon conduct after 140 minutes irradiation, while only 57% rhodium B was removed by the pure BiOBr. The corresponding fitted linear hence wood model was obtained and it is easily see the photo degradation. So this is the photo degradation of different samples and the blank under dark and then under light. These are the results. Photocatalytic activity and is the cycle. So we'll just now have a look at characterization techniques. Guys, these are the sim and team images. You can see this is the microspheres. It's 3 micrometer and it's 500 nanometer. When you make it very small, when you resolve the images with higher intensities, then you can find this is 100 nanometer sphere microsphere, and this is the team images which give you the fringes and the planes of the crystal. So this is the this spacing is equal to 0.35 nanometer and this plane is about BiOBr. 001, and the other one which we find here, the another plane, that is 012, and its d spacing is 0.28 nanometer. And this is the whole microsphere, 1 micrometer mesosphere is 500. Cementum images of A to D, BiOBr, and electron hole E to H, sorry, that is BiBr carbon quantum dot. So E to H we have to check again. E to H, E, F, G, H means the last the last four are carbon quantum dots. So these are the carbon quantum dots already introduced in the BiOBr. In the first we can see these are BiOBr just. This is XRD. X sorry, it's not XRD. We will start from the first XRD. This is XRD. The XRD data shows that there are some peaks that belongs to BI. That's 101 plan, 0112 plan, and BiOBr. These all plans, but uh, the its none peaks expected in BiOBr are these expected peaks according to the reference. But some peaks have higher tendency, some have lower tendency. Means something is a little different from the expected peaks. But some peaks which we are expecting we achieved during this synthesis. For example, the authors achieved during the system, not we. So they characterize with the XRD like this. And this is actually XPS. XPS is like elemental composition. So in XPS we can check its elemental composition. As so in survey BiOBr carbon quantum dots, we find here that one peak is very high, that is carbon, and the other peaks also get higher than the other peaks. Means their energy is increased in the carbon BiOBr carbon quantum dots. The intensity is increased, means their percentage is increased due to interactions compared to the simple BiOBr or the pristine BiOBr. So Bi4F peaks can be deconvoluted into these, and the bonds are not mentioned even. The peaks of BiOBr carbon quantum dots are divided into some sub-peaks due to some interactions between carbon and Bi, oxygen and Bi, and some more interactions existing in BiOBr carbon quantum dots. Whereas oxygen peaks can be divided into or can be deconvoluted into 5 peaks. We can observe the energy is minimized. Uh, um, the peak values also decrease in the after combination too, and here also with the combination of carbon quantum dots, the values decreased in the carbon quantum dots and BiOBr. So 3, 532.1, 531.2, 530.0, and these values were decreased in BiOBr carbon quantum dot to 527, 529, 531.2. And in the same way, binding energy for Br, Br65, 66. It's decreased in carbon quantum dots, while it is so much for BiOBr pure. In the pure form, it is more higher than in the combination form. Means when you combine the things, then electrons can be loose easily, can be excited easily. Here is the carbon uh, XPS data, which shows that carbon has 81, 82 and 85 is pure, but it has 82, 83 and 86.4 in carbon quantum dots. This is increased. Why this is increased? Because the percentage of carbon is increased there. Of course, there we add some carbon quantum dots. So means as the pure carbon, as the carbon quantum dots are increased, thus the percentage and their energies will be increased. Uh, This is UV FTIR. Sorry, this is FTIR results of the all samples. FTIR shows four distinct peaks at 510, and this is for BI and BIO, and 1388 for BICL, and 29, 22, and 34, 32. These are for OH bonds. Torque curve of BRC material is different. So these are the torque plots with the temperature and weight. Pressure P divided by P naught, and quantity of adsorbent. So this for adsorption, nitrogen adsorption, desorption isotherm. This is UV. The UV with spectroscopy. UV spectroscopy of BiOBr quantum dot material with different content of carbon quantum dots. Okay, what the main thing which we receive from this is just we have to take from here the band edges or energy absorption edges, from where they start to absorb the energy, like where they fall, HV and HV square. This can help us to understand its energy band gap. This is photoluminescence. Photoluminescence is also quite interactive. The most lowest excitation is observed in 0.6, means that is ideal one with better results. And here we can find the SAM that has highest potential compared to the other highest potential, H and HV square. So this is a review of this paper. This paper content is concerned with again here is some results of UV's absorption of the rhodium B trapping experiment by BiOBr quantum dots. Okay, the mechanism of degradation mechanism is proposed like this. For example, rhodium B and NP plus peroxide radical that will react with these compounds, and then it will degrade into the products. So the electrons can be received from the conduction band, while these can be excited to the conduction band from the valence band by excitation through the sunlight. While the carbon quantum dot can act on the near to the junction or the conduction band that can join to the conduction band and can transport electron further. So means the conduction band will donate electrons to the carbon junction and carbon quantum dots, and carbon quantum dots will excite the electrons to the further it will excite electrons to the upper part, and which can be trapped, and they will not go back. So these electrons can be while the electrons coming from carbon dots to back to the conduction band of material, that's BiOBr. It can reduce the oxygen, and the oxygen will be converted into oxygen peroxide, and that peroxide or superoxide that will react with these organic materials, then it will degrade and oxidize the organic pollutants into carbon dioxide and water. So rhodium B and palladium degraded products will be received from here through the carbon quantum dots. So at the end we will discuss in a short the better to discuss its mechanism, because mechanism give insight. Mechanism of photopollutants. In an attempt to elucidate the photocatalytic mechanism involve the photodegradation of rhodium B or BiOBr carbon dot material, a series of photodegradation experiments were performed with the sequencer to carry it out. The absorption peak of the rhodium B 553 nanometer analyzed UV visible spectroscopy indicate the reflect of the degradation efficiency after being illuminated from 154 nanometer minutes. It can be seen by the photodegraded and completed at 145 minutes illumination. When TBA electron acceptor was added into the degradation system, the demonstration of electron does not have a direct effect the photocatalyst process only. Uh, so IPA is for OH scavenger. We use here some scavengers like TBA electron acceptor, and IPA is OH sequencer was added to the degradation system, and the photodegradation efficiency was 90% obtained during 145 minutes elimination, and the indicated OH radical is not man-active species. However, the photodegradation of active decreased in the 70% during the 145 minutes elimination when potassium iodide H plus sequencer was added into the degradation system. Simultaneously, the photodegradation activity decreases by 81% when the BQ or minus peroxide sequencer was added to the degradation system. It indicates H plus and OH minus play an important role in the photodegradation process. So the base of the experiment results, the photocatalytic mechanism was proposed. Firstly, due to the superior visible light response of carbon quantum dot, the photoexcited electrons is generated with the sample is eliminated by visible light. Then the carbon quantum dots acting the electron donors and photoexcited electrons can be injected band a BiOBr, and photo-generated protons can be injected to the valence band from carbon quantum dots. Then the carbon quantum dot acting as electron donor, and the photoexcited electrons can inject it into the conduction band of BiOBr, and the photo generated H plus can be injected to the valence band of carbon quantum dots. This in this process can be done to generate the O radical, oxygen O2 radical, uh, superoxide radical, and anion radical, and secondly up of converting PL property of carbon candidate can convert the longer wavelength light to the shorter wavelength light, which can be turned excite BiOBr to form photoexcited electron hole pair. Thirdly, The formation of interfaces between BiOBr and carbon content dots, the delocalized conjugated structure of carbon content dots made it easier to transfer the electron photogenerated carriers, resulting in efficiency of electron and hydrogen pair separation. In addition to the elemental Bi particle generated BiOBr matrix during the growth process, carbon content dots exhibited superior SPR effects. SR and SPR. These are the spectroscopy further promote the formation of electron and hole pair in the photocatalytic system. Meanwhile, the elemental Bi could act as electron donor. The photoexcited electrons can be injected into the carbon conduction band of BiOBr for the RHB. Degradation of RHB could be absorbed the visible light, produce singlet and triplet states denoted by RHB, and electrons would inject into the photocatalysis system from the photosensitive rhodium B. In the process, the intermediate products of rhodium B can be oxidized by O minus in the radical and H plus transform into the ultimate degradation product. So conclusion, in summary, the novel BiOBr carbon hybrid material was successfully prepared through the facile solvothermal method followed by the hydrothermal process. The carbon dots were dispersed on the surface of microsphere like BiOBr, and a tight junction were formed. Photocatalytic activity of BiOBr carbon material on the rhodium B and the PNP degradation under visible light irradiation and increased that dramatically. The BiOBr and carbon content of 0.6 exhibited the optimal photocatalytic performance for the degradation of rhodium nitrophenol, paranitrophenol. Furthermore, the BiOBr carbon content material showed excellent reusability and stability, which was valued for the potential application of the environmental protection. They enhanced the photocatalytic performance of the BiOBr carbon quantum dots material was attributed to the excellent electron transfer ability and increased the light harvesting capacity of the carbon quantum dot. The radical trapping experiment revealed that the oxygen peroxide radical and the holes were the main active species during the photocatalytic process. This work was expected to provide appropriate theoretical references for the new development of carbon dot material based on hybrid material with high photocatalytic performance. So this was the whole summary and discussion of our today's talk and today's review paper. That today we reviewed a paper which was focused on developing a carbon carbon quantum dot material hybridized with BiOBr BIOX material. So this research paper opened a new way to develop hybrid material for higher photocatalytic performances. It has higher degradation rates and it's reusable and recyclability means it was stable for the 5 cycles. So the other parameters also observed very good results, and its XRD, its XPS, and all these parameters were satisfactory. So today's in this paper, we again for a short summary, the group of researchers have synthesized BiOBr carbon quantum dots microspheres with enhanced photocatalytic and photostability under visible light irradiation. Thank you so much for supporting and watching. Stay blessed and see you in the next uh, program with another uh, paper review. We will discuss more things, we will understand, and slowly, gradually, we'll increase our complexity of the discussion, and we will understand more things about the photocatalysis and the papers linked with the carbon BiOX compounds. Especially, this is our focus. So, stay connected, and you can write your comments on the in the comments. We will try to reply you. Thank you so much, and stay blessed.